Hey everyone, and welcome to week 10. Week 10 of the GEO101 term moves you into the unit on geomorphology. So this week is all about the Earth profile and composition. So straightforward lesson, quite frankly, but important, obviously. Building block material, literally and figuratively in this case. So the image here you see is one of the Grand Canyon. So there you have the different layers, sedimentary rock, and the work that water has done on this landscape over millennia. If you ever get a chance to go to the Grand Canyon, and I highly recommend it. It's a beautiful, beautiful, amazing place. So having said all that, let's get going. So these are the lesson objectives for the week, 5 of them. And so the geomorphology block really addresses internal versus external processes. So these next 2 lessons, this one and the following one, really address this. And then we get into how all that built up land then gets eroded away. So that's the sort of the continual building and destruction of land and land forms and landscapes over time. So again, part 1, building processes, volcanoes, tectonics, all that kind of thing, how the earth shapes and changes shape over time. And then of course, part 2, or the more encompassing part, dealing with water, wind, gravity, water in the form of ice and snow, meaning glaciers, and wind in deserts, and waves near coastlines. So that's really part 2 of the block. Geomorphology versus geology. Geology is the study and the origin of, the rocks, the structure, the materials. Geomorphology is literally studying the shape of the earth and how that earth changes. So for example, based on earthquake activity, volcanic activity, water, wind, rain, glaciers, landscapes change over time. Think about New York and New York State and New England. It's basically a glaciated landscape that has changed a lot in a very, very long history. The internal structure, of course, we're used to the crust. That's where we live. That's where the biosphere meets the hydrosphere and the atmosphere, but the lithosphere, or the crust, is the very, very top. And then you have the different layers, the upper mantle, lower mantle, liquid outer core, and solid inner core. And that is what makes up really the majority of the volume of the planet, which we never get to see, thankfully. So how do we know what the Earth is like underneath? Well, there are several ways. You can do things like seismic wave analysis. You can look at what comes out of volcanoes and the different kinds of volcanoes that you find across the Earth. You can pretty much figure out how the difference between continental crust and oceanic crust, and they're very different. So one of those aspects would be internal to the Earth, and that is earthquakes. Obviously, you just think of that as a very simple shaking of the Earth, but they generate pulses of energy called seismic waves. And these seismic waves are either deflected or refracted, bent, as they travel from their original source through either less or higher density material, and whether that material is either solid or liquid. And so you have first surface waves. These obviously travel along the surface of the planet. They're responsible for the majority of damage during an earthquake, okay? And again, they only travel at the very, very, very top. P waves, or primary waves, are the ones that basically, think of them as a big, like an accordion, compression. And they travel through both liquids and solids. Whereas S waves, or secondary waves, travel only through solids, not through liquids. Okay, and understanding of S waves, P waves, and surface waves allows you to understand what the inside of the Earth is like. You can map it. So when it comes to the different kinds of crust, you have thick but less dense continental crust, and you have thinner but heavier or denser oceanic crust. And so continental crust is light in color. It is made up of quartz and feldspar, and it has a density of around 2.8 grams per cubic centimeter. So every little cube, it's like a cube of sugar. You want to think of it in that size. Every little cube of sugar or cube of continental crust is that dense. So here's an example of continental crust in the middle of Canada, Jasper National Park. Now, oceanic crust is what's called mafic, which is magnesium and iron rich. And it's usually dark in color and denser. So instead of 2.8 grams per cubic centimeter, it is 3.1. Now that difference doesn't seem that big, 2.8 to 3.1. But think about the trillions of cubic centimeters out there. And that adds up very, very quickly. So here's an example of boulders made up of basalt, which is this mafic material that comes out of a volcano in Hawaii. The crust of the Earth is unique in that it is, if you remove the water from the oceans, it has its own set of features. There's high relief, low relief, shelves, mountain chains. They just happen to be underwater. And so let's look at that and let's examine it. So the crust is subject to weathering and erosion. So weathering is the physical and or chemical breakdown of rock, and erosion is the removal of that weathered rock by the force of wind, water, or frozen water, ice. We'll talk about the idea of the relation of the Earth's structure to plate tectonics and how these plates are basically floating on top of the more molten material underneath. And over geologic time, these have moved and shifted with respect to one another, forming the landforms that we know of today, like the Rockies and the Andes Mountains in South America, and the Himalayas between Eurasia and India. And here's an example of continental crust versus oceanic crust. Continental crust, alpine chains, continental shelves, whereas the ocean has mid-oceanic ridges, continental margins, trenches, and volcanic hotspots. Okay? So here's an example of like the North Atlantic. So if you were to take a line from, say, New England all the way to Northwest Africa, what you find is basically that line would be this right here, and this is what the ocean bottom would look like. So there would be a mid-oceanic ridge, and there would be a big plain sort of in between there and here. This would be New England. This would be Northwest Africa. This point corresponds to this. This point corresponds to that. And so that brings us to the issue of rocks versus minerals and what the difference between the two of them happens to be. And so a mineral is naturally occurring. It is inorganic. It has a distinct chemical composition, whereas a rock is just a combination or an aggregate of mineral particles. And it's broken down into the three that you've heard about before in probably 8th grade earth science class: igneous, sedimentary, and metamorphic. So the properties of minerals: composition, color, hardness, and the luster. Now, the three types of rocks, igneous, imply the issue of whether they happen to be, whether they form inside or whether they form outside whether you address them as intrusive, which is called plutonic, or extrusive, meaning volcanic. And if you've been watching any of the volcanic activity that's been happening in Iceland and in the island of La Palma in Spain or in Hawaii, that is mostly extrusive material because you're literally seeing it form outside. It isn't forming on the inside. And there's a big difference. So here's volcanic, here is plutonic. Inside, outside. So intrusive, they tend to have large crystalline structure and they tend to be stronger, bottom line. So granite would be an example of this. And granite is what you will use inside in your kitchen, and it's there for a reason. And here's an example where you tend to find seldom. Some of the more unique batholiths, sills, dikes, and laccoliths, and how they form. Your book addresses the formation of each of these. But again, these are intrusive igneous rocks, meaning they formed inside, underneath the surface of the earth, and at some point they may have been exposed to the outside. Intrusive, under the surface. So here's an example of an intrusive, what's called an exfoliation dome. This formed under the ground and then was exposed. And so this is one big giant chunk of granite. The idea of exfoliation is the fact that the outer layers will peel away from the rest of the material when the confining pressure is released. And if you go back to this image here, you can see the different layers, almost like little peels, like an onion. You can sort of peel them away. Extrusive, well, here we're talking about cooled quickly on the surface, providing a smaller crystalline structure. They tend to be weaker. And these are some of the most common examples. So just like granite is the most common intrusive igneous rock, basalt is the most common extrusive igneous rock. So think about what you're seeing. Again, if you've seen any of the volcanic videos from Iceland or Hawaii or La Palma in Spain, that is all basically basalt, very dark colored rock. Here's an example of basalts. Sedimentary rock, as the name implies, is rocks that are formed from the accumulation of sediment that has been compressed and cemented together. So these rocks tend to be less strong, although, you know, some of them can be pretty hard. So the issue of cementation is addressed as lithification. So when you lithify something, you take everything and it's almost like you glue it together. Okay? And so that's how sedimentary rocks tend to form. The issue of deposition followed by compaction and cementation will lead to this process, which is when they basically form into an actual rock. And you tend to find rocks like shale, sandstone, and limestone. And here's some examples. Notice the little bits of material inside the rock. So you have two types, clastic, made from materials of other rocks, and non-clastic, made from organic depositions like seashells, that kind of stuff. Here's an example of sedimentary rock that has been tilted by forces applied onto that. There you see the different layers. And so these are obviously the harder material, which over time has been eroded away. Metamorphic rocks implies change. And basically, originally igneous or sedimentary, you can basically alter them by adding heat, pressure, or both until they no longer resemble what they were originally. So the best example of that is marble. Marble used to be limestone, but if you apply enough pressure and heat, you get a much harder, much more durable material. Again, the application of pressure and heat. Here's an example of basalt. It's a molten material at one point which flowed over non-basalt material. Notice the part that was changed has a different color, and then that heat was insulated from the material below, and this is not metamorphized. So here you get to see three kinds. You get to see igneous, you get to see sedimentary, and you get to see metamorphic, all in the same layer. And here's another example of material that has been altered. So these are some of the more common metamorphic rocks: sandstone to quartzite, limestone to marble, shale to slate. And you can sort of look at the rock cycle on your own. Like anything, it means you can take igneous and metamorphic and wear it down, recombine it into sedimentary, take that sedimentary and apply heat and pressure and turn it into something metamorphic again. And the cycle sort of repeats infinitely over time. All right, and that's frankly the lesson. That's it. There's really not that much to it this week. Next week, we'll address the issue of lithosphere and tectonic processes. So, for example, in the image here is the mountain known as Mount Fuji, just to the southwest of Tokyo in Japan. And Mount Fuji is a very specific type of volcano that is found along a specific type of plate tectonic type of boundary. And it looks the way it does for a very, very specific reason. So having said that, I hope you have a great week. And if you have any questions, let me know. And look forward to interacting with you soon. Bye.